Good morning, good afternoon, good evening, based on wherever you're joining in from. Hello, I'm Hamza, an applications engineer at Erith Group, and welcome to this webinar on Flange installation and management. I'll just start the presentation right away. Okay. So I'll walk you through the agenda. First, to understand how a Flange installation works, we'll go through in a stepwise manner. We'll go in 7 steps. The first would be we'll talk about this how to break the system, how does a pipeline opened up. The second would be the flange. We'll talk about the flange and then we'll talk about the gasket. We'll go through the bolts and how an inspection is done on the bolts. Then we'll go through the assembly, and then we'll talk about installation. And again, we'll talk about the system patch up. We'll be talking about cost-effective strategies and ingenious tips all throughout the presentation. So the first is the system break. Even before we begin the operations, I would like to talk about the safety measures that need to be used. We recommend to always wear proper personal protective equipment and follow lockout, tagout procedures, as well as other companies' safety policies or procedures when performing work on a flange connection. So going ahead, for the joint opening operations, we have 6 steps. Now, the first step is to basically have a clear objectives in mind before starting the operations. A clear set of objectives are necessary before starting joint opening operations. This gives a better understanding of the job and the tools that you need to require, whether it be installation of a new gasket or pipe cleaning and maintenance like pigging or cardboard blasting, or whether it be just blinding operations, blinding the flange for other operations, basically. So we need a clear set of objectives in mind. We need to have a permit. A permit shall be opened by the operations team. So our next step would be to secure the work permit for the job. The permit to work shall be opened by the plant operations team. And then we need to isolate the system processes. Basically, you will need to correctly identify the exact location in the pipeline or system where you need to work, either through the isometric drawings or process and information diagrams, or as directed by the site engineers, basically. Once you know the exact location that you need to work from, that location has to be isolated from the entire system processes so that you can safely work on the system. And make sure you perform all lockout, tagout procedures. The work location needs to be completely isolated from the system. Again, we have the de-energizing of the system. This needs, the emphasis that we make on de-energizing the system is, even though it's always talked about in the industry, in the aspect of safety and in the aspect of human lives that are involved. De-energizing is very important. We need to depressurize and drain the fluid whenever required. We need venting in case the fluid is gaseous. So it is a very important part of the starting the joint opening operations. The pipe and flange spray accidents are not uncommon. So we recently came across a case at one of our clients' installations where a flange opening incident caused the fumes of carbon monoxide to be released. It did have a lost time injury. Thankfully, the incident did not have any casualties, but yes, it was reported and classed as an LTI incident. So we need to avoid this at all costs. It's a simple thing that we need to keep in mind, but yet incidents do happen. So the next step would be the purging and decontamination. If the line that you're working on has previously contained toxic fluid or SAR stock, you should wear an air supplied respirator in the positive pressure mode. And proper verifications have to be done after the purging and decontamination. We shall begin work only after gas testing is complete in case of toxic process fluids. If the line that you're working on has contained toxic fluid, again, you need proper equipment for that, proper protective equipment for that. Um, basically, the different purging methods can be used. As we're talking about pipelines specifically, and in general terms, displacement and dilution purging are the two major type of purging methods that are used. The vacuum purging is generally used for dead spaces, and since pipelines are generally not dead spaces, so we do not require vacuum purging. So going ahead, is the actual breaking opening of the flange. This is when we open the bolts, and basically we have finally opened the pipeline. So we need to keep in mind that it's the bolt load that keeps the fluid sealed, not the gasket alone. Your gasket is as good as the bolt load that it is applied, as good as the bolt load that is applied to it. So once you lose the bolt load, the hydrostatic end forces are going to try and remove the flanges apart, and you will have the fluid leaking out. You have the fluid coming out. So it is always recommended to use a splash guard during bolt opening operations. It is always safer to loosen the bolts on the side of the flange opposite to you first. Uh, we always recommend using a splash guard. One more thing is it is a good practice to record the opening torques of the flanges, just in case the torquing values are not available. Basically, when dealing with non-critical media applications, or when pressures and temperatures are low, and when the gasket being replaced has the same make and model as the one being removed from the flange. So in this case, you can record this data. What you need to do is you note the torque that was required to unscrew the nut from the flange assembly. This simple practice can save time and effort. Basically, this data, if recorded, can also prove to be valuable if it turns out that the gasket condition is concerning and it's undesirable. If the gasket has some issues and there is a need for an investigation. So this data can come in handy for those engineers also. So moving on to the second stage, that is the flange. So before assembly is started, we need to clean and examine flange and contact surfaces. Um, uh, there are a few in terms of cleaning. There are a few exceptions that are held in ASME PCC1 guidelines. Otherwise, we need a completely clean flange to work. For gasket installation, the gasket contact surface need to be cleaned. You can use solvents. You can use soft wire brushes to clean the surface from contamination and damage. Needs to be inspected. Um, Again. So we'll have four steps for flange preparation once the flange has been opened. The first would be to remove the gasket removal. We need to remove the gasket entirely. As you can see on in the diagram on the right hand side, you have there is gasket residual on the serration of the flange raised face. Be sure all material is removed from the flange faces. It is important that the previous gasket to be completely removed, including any residual flakes, chips, or fragments. The only exception that I was talking about, made in the as in PCC1 guidelines, is that you can have a residual flexible graphite on the flange surfaces, on the seating surfaces. Other than that, if it's any other material, it needs to be completely removed. We need a completely clean flange to continue our operations. Again, as you can see, there can be apart from the previous gasket, there can also be corrosion and debris on the flanges. We need that also to be removed using different types of methods. It can be soft wire brushes. It can be a basic scrubbing material easily available there, in the toolbox. We do not even the as we PCC1 guidelines do not recommend using cast iron brushes over steel flanges. So due to the hardness, the difference in their hardness, it is not recommended. Next comes the surface finish and the flatness. So, so as you can see in the diagram, there is a flange which is severely has an accelerated corrosion on its face. You can see that due to corrosion, the entire raised face has been deformed, and the flatness is lost here. Again, this can result in low stresses on the gasket inside diameter and considerably higher stresses on the gasket outer diameter, which may result in the gasket getting crushed because all the compressive forces will be directed at the outer diameter, and that can cause catastrophic failure if this gasket is put in an installation. It is important to check the serrations on the raised face of the flanges for proper sealing of the gasket. These serrations bite into the gasket and help create a good seal. So it is very necessary to have the right surface finish as well as the serrations. So the arithmetic average roughness height needs to be checked. It is measured in micro inches. So a serrated finish, either concentric or spiral, is required with 30 to 55 grooves per inch, and a resultant roughness between 125 to 500 micro inches. So this allows for various grades of surface finish to be made. Available by this data is generally available by the flange manufacturers for the gasket, um, for the contact surface of the metal flanges, basically. So your typical standard on ASME is the ideal surface roughness is 125 to 250. So these serrations are needed so that it can bite into the seal and retain the gasket material. However, the API 6A or the RTJ flanges, they have smooth faces. They do not have serrations. Um, Going ahead, we do not need very high roughness on the flange faces because a very high arithmetic average roughness height, like above 500 micro inches, it will be too aggressive for the gasket and the seal. It can damage it, and that can cause that can probably cause under compression that can cause the gasket to fail. So yeah, perhaps no flange issue is so common or as critical as ensuring proper alignment of the joint before tightening. So this is easier said than done in the field. Proper alignment is a very difficult task. The riggers and installers have a better understanding of the challenges that come in pursuit of perfectly aligning the flanges for a good installation. So there are different types of flange misalignments. There are lateral misalignment where the axes are parallel to each other, but they do not meet. There are angular misalignment where the axes are at an angle to each other. This can again cause very high stresses while bolting the two flanges together with a gasket. That can have very high stresses on the gasket at one end and relatively very low compressive stress on the other, and that can cause a leak path to generate on the other side. Again, there are flange gap. If there are if there's a too large of a gap between the two flanges, again, that will require it to be aligned perfectly. We do not need too high or too low gap between the flanges. We need enough flange gap so that we can put the gasket in place. And speaking in general terms, the thickness of about two gaskets is in terms of layman terms, it is a good enough gap. So talking about torsional misalignment, it can be identified when the axes of the flanges are aligned, but the bolt holes are not aligned. In extreme cases of torsional misalignment, you will have to get a new pipe if possible. So this kind of a misalignment cannot be uh, corrected easily. So in case it's a bulky, it is connected to a bulky equipment or it's a part of a process system, then there is not much you can do besides cutting the flange out from the pipe and realign it correctly and then perform a field welding. So it's like a very drawn out process once this kind of a misalignment comes up in your installation. It's perhaps the most troublesome type of misalignment. So Going ahead, again, as I talked about this center line high-low type of misalignment, again, the parallelism, excessive spacing. So now talking about the gasket failures caused by the flange conditions. So here we have an example. On the right, you can see a gasket failure. These gaskets have been in a 150 pressure class 1-inch race space flange. So we know that the compression at one end was about 1% and the other end was 31%. This can be due to this variable compression range occurred due to the flanges not being properly aligned, the flanges being at an angle to each other. So there was very high compressive stress on one end of the on one end of the gasket and very low on the other end. Again, we have another example here. The compression at the inside diameter of the gasket was about 1.6%, and the compression on the outer side was from 11 to 15% at the outer diameter. So again, talking about the flanges, should a flange ever fail, the exact same flange can theoretically be ordered to replace its predecessor, but a root cause analysis should be conducted on any flange that has failed unexpectedly. If the cause of failure is not determined, the same failure may occur again, even with a new flange. So it is very necessary that a root cause analysis be conducted on any flange that has failed unexpectedly. Now moving on to the stage 3, we have the gasket. So basically, we need to know the gasket selection criteria. There are a few basic data that needs to be evaluated, that needs to be analyzed in order to select the perfect and most effective gasket for the use. So for a suited gasket for a required operation or service can only be selected once we know the temperature, the application, the media flowing in the system, media flowing in the line, the pressure of the system, and the size of the flange. Basically, the size is one of those things that is readily available on the flange itself. So until unless it is a non-standard flange, the size is not usually an issue. That this data is easily available from the process system. Um, the gasket needs to have we need to have the information regarding the temperature, the continuous operating temperatures, the spikes in temperature, if any, or if there is thermal cycling occurring in the system. So these criteria need to be evaluated for to find a gasket that is compatible with the type of application. The other thing would be the type of flange, basically the application of the gasket, the equipment that is going to be the gasket needs to go into a kind of equipment, and if it is a boiler or if it is a reactor or if it is a simple pipe flange, we need to know the kind of application that the gasket is being utilized for, so as to select the perfect material for the gasket. The other is the media. We need to know the media flowing in the piping system or the process. If what's the pH of the media? If it is an abrasive media, we also need to know the chemical compatibility of the media with the gasket that we need to select. So that also plays a very important role in the selection criteria. The next is the pressure itself. Again, the pressure of the system is already defined. We need that data from the system so that we can select the proper gasket. So once you have the gasket in the field, you need to do three basic examination on the gasket. You need to check the inside diameter, the outside diameter, and if the gasket has been damaged from shipping. So you need to check the diameters, the inside and the outside diameters of the gasket to ensure that that you have the right gasket with you to go inside the flange. If you do not have the correct gasket, there's no point opening a flange up without having the correct gasket to replace the one that is already inside the gasket. So Talking about gasket failures that occur due to damage, is if you have a damage on the surface of the gasket, it can cause a leak path for the fluid inside, and this is where the failure will occur. So it's very necessary that you have that you inspect the gasket before installing it. So now I'd like to ask you a question. Like, which system of measurement is prevalent in your industry or your company or basically your installation? Which type of measurement is used? Is it metric? Is it US customary units? Or is it imperial? I'd like you to put in your responses. So I see. Most are using metric system, and we do have a few with the US customary units and a few responses that they have no idea what kind of measurement system is being utilized. I see. And I see that there is no response for the imperial system of measurements. That was quite expected, but yes. Understood. So going ahead, we have the gasket data. As you can see, we have the continuous operating temperature of a gasket. This is the gasket data that we provide with each and every gasket that we supply to our customers. We list the continuous operating temperature as well as the maximum and the minimum temperatures that the gaskets can handle. So the gas here the temperatures are given in degrees Celsius as well as degree Fahrenheit. So you can have both of these measurement. We also have the maximum pressure that it can handle as well as the minimum pressures. The ideal operating limit is also mentioned with this data. So one thing that needs to be kept in mind is that while selecting a gasket, you need to have a proper understanding of the pressure and temperature multiplier. So the pressure and temperatures cannot they simultaneously make a lot more sense because standalone a gasket at a higher temperature cannot work at a higher pressure as well. So there is a correlation between the operating pressure and the temperature. And so the operating temperature of your system and the temperature of your system when multiplied must be equal or lower than the pressure and temperature rating of the gasket. We cannot operate at maximum pressure as well as the maximum temperature at the same time. So as you can see, this is our Garlock's Blue Guard Style 3000, which has a pressure and temperature multiplier as 12,000 when talking about metric measurement systems. So you can calculate your application data. From your application data, you can calculate your operating temperature and pressure, and we can arrive at the suitable gasket that is perfect for your application. Since there are many different kinds of brands that are there that may or may not provide the complete set of data regarding the maximum and apart from maximum minimum temperatures, what is the continuous maximum that it can work at, what are the ideal operating limits of the pressure. So for this, I can introduce you to other sources like the gasketdata.org. It is necessary to be aware of accurate gasket data to accurately select and install the gaskets. This website shall give you a great amount of data on most available brands of gaskets. However, all the gaskets that we provide, like any other product that Erith provides, comes with installation support if required, and we can provide the torque values for our gaskets. Um, so talking about the gasket dimensions, These are the ring gasket dimensions as shown in the table. But why do we need to know the gasket dimensions? Basically, flange class does make a difference. Why? Because the gasket dimensions for a particular flange class for a particular flange size will not be same as the other uh, pressure class of flanges. So it is always a good idea to have the correct gasket dimensions, data of the correct gasket dimensions, so that you can compare. We can check to make sure the gasket is properly centered by checking if it perfectly holds over the bolts, the lower bolts of the gasket of the flange, and the gasket ID should perfectly match with the ID of the pipe. If that's not the case, then you know that you do not have the correct gasket for the type of flange that you're working on. Some failures of an incorrect type of gasket being selected can be due to overcompression. This is Garlock's Gylon 3504, a type of gasket which has been overcompressed in a glass line reactor. So we can see concentric splitting here due to overcompression. This is probably due to improper installation practices where the torquing values as recommended by the gasket provider was not utilized by the people installing the gaskets. Another gasket failure for over compression. Even though this time the installation was done correctly, this time the gasket was not selected properly, and it was a rubber gasket that was used in raised face flanges, which is not the correct type of gasket to go in a raised face flange. So again, you can see concentric splitting in the gasket. This is due to overcompression. A general rule for material selection that we have is that raised face flanges work well with compressed non-asbestos fiber sheets, with the Gylon range of products, the PTFE gaskets, the graphite gaskets, the metallic gaskets. Once you have flat face flanges or full face flanges that are there, we need full face gaskets for those, and rubber gaskets work well with that. Or we also have a product line for the gaskets called the stress saver. So these go well with the full face. So we need to talk about the creep relaxation and fold flow. This is a phenomena that deserves special attention. It is also called creep relaxation, and it is a major cause of bolt load loss and results in leaking joints and when the soft gaskets are utilized. When soft gasket material are first put under load, they initially resist the compression. However, within a few minutes to a few hours under load, they tend to flow away from the pressure, permanently thinning and causing a corresponding drop in the bolt loads. Each type of gasket has its own creep factor or percentage of load loss. Consulting the gasket manufacturer's literature or consulting directly with us, we can provide with our technical service. We can determine these values. Um, Creep generally happens within the first 4 to 6 hours of assembly, so it generally does not repeat. So because the gasket material reaches a stable density and does not resist further thickening and resist further thickening, we can just retighten in the bolts and have the required bolt loads over the gasket material. So now talking about the bolts that actually provide the bolt load to the flange. So once you have the bolts removed from the flange, you need to inspect the bolts. You need to check whether the bolts are the correct grade for the type of flange and the type of piping system that is there. You need to check the thread condition of the bolts. You need to check the thread pitch. Also, you need to check for the lubrication that needs to be applied over the threads so that there is smooth tightening of the bolts. You need to check if there is any volumetric change in the bolts once it has been removed. If you find any volumetric change in the bolts, that means they have been is, stretched beyond their elastic limit, and this is when you need to get new bolts. You cannot use those bolts again. Um, and again, if the threads are damaged, you need to get those bolts changed. Ideally, we would want the use of fresh and new bolts at every flange connection when installing a new gasket. However, understandably, in practice, the bolts are reused, and it becomes ever more important to closely inspect the bolts if they are being reused. There are multiple different types of material for the bolts. We can talk about the general processing, general process bolting materials. We use the ASTM A193 grade B7 stud bolts along with the corresponding ASTM A194 grade 2H nuts. So this is for general service. It can handle that. It is generally advised to use it in the temperatures of -20 to plus 450 degrees Celsius. Other bolting material for low temperatures can be ASTM A320 grade L7 with the corresponding ASTM A194 grade 4 or grade 7 bolts. This can go for -18 degrees to a -101 degrees Celsius. Correspondingly, we have grade 7M studs and grade 7M nuts for temperatures from -18 to -73. Similarly, we have many other material and many other grades of bolts for different types of applications. There are other bolts for high temperature applications. We have B8 class 2 bolts for temperatures over 650 degrees Celsius. That are very high temperatures, and these are strain hardened bolts. Again, uh, for SAR service, we have grade B7 stud bolts with 2H nuts. Also, we have B7M ASTM A193 grade B7M bolts and grade 2HM nuts, which shall be used in direct exposure to SAR environments when the bolting is buried or insulated, or when the flange is equipped with flange protectors or otherwise deprived of basically direct atmospheric exposure. So we do have many other types of machine bolts, and we need to select the correct bolting material that is required for your applications. So once we have your process data, the data of the equipment that is that these bolts are going to be utilized, and we can work and analyze this data and come up with the perfect bolting material required for your application. One other thing that needs to be done, apart from the selecting the material, we need to have the perfect length of the bolt. So the stud bolt calculation is a very simple formula. A bolt has to have enough length to go through all the parts of the assembly of a flange connection. It needs to go through the length of uh, the gasket thickness. It needs to go through the standoff that we leave as for different types of inspection process purposes. It needs to have go through the nut height. It needs to go through the washer thickness. And also flange thickness is something that it goes through. That's the most amount of thickness that the bolt goes through, as well as the height of the race face. So the formula is very simple. The length of the stud bolt is equal to the gasket thickness added to twice the number of so twice the thickness of the standoff, the nut height, the washers, the flange thickness, as well as the race face. So it's a very simple calculation that can be done in the field itself by the installers, and this calculation, if we are providing the gaskets and as well as this data, so this calculation is something that we do and it's checked before providing it to the customer. One advice that we would make is to always cut the end of the bolt which is not stamped while cutting. So once you have the length of the bolt that is required, you do not want too long a bolt to be used in a flange connection, because it can, first of all, it can be cumbersome to work on it. And the next time you try to remove them, the nuts will have a hard time getting out of the bolts. When you're threading, trying to thread it out of the bolts, it may have grit and dirt and other undesirable material on the threads, and it can cause a headache while removing them. So whenever a need arises to cut the bolts shorter than the available length, always cut the end of the bolt which is not stamped. It makes it easy to identify the type of bolt for the next person responsible for installation, disassembly or reassembly of the connection during the next scheduled maintenance check. Or think about the next person responsible for the job, and let's not make the task difficult for them. So we need to install the fasteners using hardened flat washers and thread lubricant. So we apply the lubricant over the thread, and the lubricant should cover the threads, as well as a little more lubricant should be seen above the thread height. So this is the perfect type of application of threads. Apart from that, we lubricate the face of the nut that is going to be in contact with the washers, and this basically causes also protects the nut and the nut bolts and the washers from getting abraded among themselves, as well as reduces considerably reduces the amount of torque that is converted to bolt loads when these nuts are tightened. So let's talk about the assembly. So we have talked about the flanges, the washers, the nut, the bolt. We need to have a correct understanding of how these are arranged in a flange assembly. So as you can see in the diagram, we have an sort of exploded view of the flange assembly. We have the two flanges. We have the gasket in between. We have the bolt rod, which goes through the bolt holes. We put the nut on either side of the nuts on the either side of the flanges. In case of if the joint is an isolation joint, we also have a sleeve that goes through the bolt. We have washers. In case of an isolating joint, we can the one washer can be an isolating washer, the other can be a steel washer. So this is a basic diagram of a flange connection. This is an exploded view, and now as you can see, this is when the isolation joint or a flange joint has been assembled. So as you can see here, you have the two flanges connecting in the center. Inside the two flanges is the gasket. Just between the flanges and the nuts, you can see the two different types of washers that are there. The insulating washers is towards the flange, and the metal washers is towards the nut. Um, Going ahead, I'd like to ask you to basically join the two flanges together. We torque the bolts. Which torquing values are applied when closing a flange at your industry? So I'd like to know what kind of torque values are utilized. I see, I see. So basically, most people are using the manufacturer provided values. So it's a good practice. It is the best practice to use the torque values that are provided by the manufacturer of the gasket. In some cases, as I have seen, there are company standard values that are used. Which is not a good position to be in, since different type of gaskets can have different material structure, different compressive stress, and yield strength. So it is not a good idea to have company standard values until unless you have taken into account the kind of gasket that is going to be utilized all throughout your process system, which is rarely the case. So it's always better to have and utilize the manufacturer provided torque values. So yeah. So going ahead, we need to see the different types of uh, parameters that we need to check while putting a flange together. So higher friction between two sliding surfaces requires more force to push the surfaces past each other. What does this mean? This basically means that if our bolts and nuts are not lubricated properly, they'll have a higher friction and more torque will be required to attain the same amount of bolt load that would have been achieved if the lubrication was properly done, and the less amount of torque would have required. So higher friction between nut and bolt threads require more of the applied torque to be used to turn the threads, and less of the applied torque is used to tighten the bolt and generate preload. So the same amount of bolts can cause say same amount of torquing values can cause different preloads to be generated in the bolts. So once we have dry threads, the value for the coefficient of friction, the bolt coefficient that we have can be 0.16. The lubricated threads have 0.12, and PTFE coated threads have 0.08. So we have to take this into account while calculating. As a manufacturer of gaskets, we take this into account while we calculate the torque values. So make sure torque value calculations reflect what is being used on each assembly. If the calculations are being done at your end, um, uh, since we are already taking this into account when we calculate the values for these bolts. So the industry accepted approximation for K is the friction coefficient, and we add 0.04 to it. We can look at a few examples to understand how this actually affects that a bolted assembly. So for a 3-inch 600 pressure class flange using B7 studs, calculated assembly torque was 209 foot-pounds. The friction coefficient when it was a dry assembly, it was no lubricant was used. The net factor being 0.2, 50 KSI bolt stress was generated. And when PTFE coated bolts were used in place of dry studs, the same amount of torque being applied uh, had a very low friction coefficient of 0.08, and the nut factor being 0.12. We had 84.4 KSI bolt stress generated from the same amount of torque. So this is how the friction coefficient has a very big say in what amount of preload is being applied to the gasket. So going ahead, there are different types of tools that are used for torquing. Most common is your torque wrench, the handheld torque wrench that is used. We also have hydraulic torque equipment that we see in the industry, and tensioning equipment also. So all these are perfectly fine to work with the gaskets that we provide, as well as most gaskets that are available in the market. These are perfectly fine. All three different types of equipment work well. However, we do recommend that you never apply anti-seize to the gasket surface. Since a proper installation of a gasket works, a gasket provided by Garlock, all the Garlock gaskets are coated with an anti-stick coating. So you can rest assured that they will get removed easily when you open the flange in the future. You will have to deal with you will not have to deal with residual from a gasket sticking to the flange face. So there's no need to apply anti-seize, since we have seen failures due to anti-seize being that they have lubricated the gasket in the flange seating surface, and that have caused the gaskets to get crushed under the same load. We can look at few examples of gasket failures. Here we have a gasket which had gasket was where the gasket was coated with a sealant before installing it into the flange assembly. Here the proper installation, proper gasket stress was applied using the proper values for the proper torquing values. Even then, the gasket got crushed because there was a type of sealant that was used before the gasket was placed in the flange assembly. Um, so another example here would be this example is from for Gylon 3500. It was 1/16 of an inch thickness gasket that was utilized in a 2-inch 150 pressure class race face flange. Here everything worked perfectly fine. It was the temperatures were fine for the gasket. The media was perfectly compatible. The chemical compatibility was fine here, and the pressures were not too high. They were also within the range. However, we had seen a compression of 2% to 13% on the gasket, and this was due to the gasket not being compressed enough. Then not being enough bolt load on the flanges, and this caused the media to basically deform the gasket in one direction and created itself a leak path. And here, this is where the gasket failed. So it is very important to have the correct torque values and uh, uh, to install the gasket with proper torque values. So, but yeah, the question remains, how do you keep the gaskets from sticking? So the possible solutions can be to use graphite, sprayable graphite, or other lube that are available. You can use tetrafluoroethylene spray-ons, but it is recommended to avoid other types of solutions. So, how do we basically apply the lubricant? So, the lubricant application is done onto the threads. As I said, the lubricant should completely fill the threads, as well as there should be some amount of lubricant coming over the top of the thread height. Once that has been done, you can screw the nut onto the bolt. Once you have that kind of an assembly, you can put the metal washer towards the nut, and then you can put the insulating washers. This is the sequential manner in which we generate this bolt assembly. An incorrect order would be to put the insulating washers first and then putting on the metal washer. This metal washer will come in contact with the flange. And if it's an insulating joint that you are trying to assemble, that this can cause a possible electrical short with the steel washer coming in contact with the bolt threads and creating a leak path from the flange over to the bolts and to the other side. So it is one thing that you need to keep in mind. Another a solution to this kind of an issue is to use coated metallic washers. There's no particular sequence for that. You can put both the washers together. Coated metallic washers can eliminate the possibility of an incorrect order of washer placement onto the bolt assembly. So going ahead, we can put the sleeve over the bolt. If it's a insulating bolt assembly that we are trying to create. Now going on to the installation of the flange itself, I'd like to show a simulation in which can give you a better idea of how the two flanges are basically put together. Yes. First of all, what we do is we place the two studs into the bottom holes of the flange. These two studs will center the gasket between the flanges in the next step. When properly cut, a standard ring gasket will center itself in the flange assembly by touching the inside edge of the bolts or the studs. Then we pull the other flange to bring the assembly together. And then we add the remaining studs to the assembly. The two flanges are generally not this so apart, just for the sake of animation that we have done this. Then we add the two washers to either side of the studs in the assembly. Washers along with thread lubricant help reduce friction between the nut and the flange face by acting like a bearing surface. The friction can negatively impact how much force is generated in the bolt through the torquing of the nut, as we discussed earlier. The nuts can now be threaded onto the studs. Uh, when torquing fasteners in a flange assembly, it's important to apply the torque in multiple steps with a cross pattern. So Garlock and Erith, we recommend a minimum of 1/3 increments. For example, if the target final torque for the assembly is 100 foot-pounds, the first pass should be 30 foot-pounds, followed by a pass at 60 foot-pounds, and similarly. So, sorry. I think there's some issue with the simulation. So yeah, finally, when we have for the first 1/3 of the increments, we have bolted, we have torqued the nuts. Then comes the second uh, intermediate basically, the first pass should be 30% of the targeted torque. The second can be the 60% of the targeted torque, and the final can be the target torque of 100%. This method helps create an even compression across the entire gasket. Um, Now you can begin the torquing procedure in a cross pattern, applying the initial 30% of target torque. In a real installation, the torque wrench makes an audible click when the correct torque level is achieved. So you do not have to wait or you do not have to check for what kind of value you have reached. I'll again try to check if we can play the. Yeah, I'll explain the torque levels that we have. We first set the torque level to 30% of target torque on the torque wrench, and we go in a cross pattern and apply the initial torque of 30% to each nut in a cross pattern. Then we set the torque level to 100% target torque, and again use the same crossing pattern. Finally, we tighten each nut in a clockwise or counterclockwise direction to ensure all bolts are at the desired 100% of target torque. This step will also account for any loosening that may have occurred due to elastic interaction or cross torque between the studs. Um, so in a real world application, to optimize the performance of the assembly, the nuts should be torqued 12 to 24 hours after initial installation to account for the assembly relaxation. However, we do not recommend the retorquing hot. We do not recommend hot retorquing, hot bolting, or a pressurized flange connection. So as you can see in the simulation there, we are the nuts are being torqued in a cross pattern uh, uh, where the nuts are diametrically opposite to each other are tightened in a sequence. We set the torque at first 30 foot-pounds, then the 60 foot-pounds, then the 100 foot-pounds if it's a 100 foot-pound target torque in that manner. And we torque the nuts diametrically opposite to each other. So again, one advice would be to facilitate inspection. Marked ends of the bolts and the nuts should be on the same side of the joint and should be facing outwards. So basically, it's always better to install bolts and nuts in this way so that it facilitates inspection. and it's easier for the next person to know what kind of bolt material, bolt grade was used. This is something that makes it easier for the other person. So again, the question remains, how do you hold gaskets in place during installations? Again, as I told, there are different kinds of spray adhesives. And from the field, we know that there are few methods that ingenious ways that the installers have come up. They use to tie a piece of sewing thread between the two bolt holes to keep the gasket from falling over. They keep the gasket in its place. They put this thread around. Once they've pulled the two flanges together, they just cut the thread and they pull the thread out, and hence they have the gasket perfectly placed. However, we do not recommend, and it's a strict no-no, that you use tape to put the gasket in place. Do not use tape to put the gasket in place. The tape ends up being a leak path, and this can cause a failure in the gasket. As I could not show you the uh, uh, proper tightening sequence, here we use a finger tightening method for the bolts, diametrically opposite to each other. We tighten them snug or to the flange, and this way we have this all the bolts which are tightly snug with the flange. There are different types of flanges, and the cross pattern for these flanges and the number of bolts and for the different sizes are available in the PCC, ASME PCC1, for different types of and for the different number of bolts. This pattern can be taken from the ASME standards, and it can be utilized as such. We also provide this installation instructions if the customer asks from us, and these diagrams and the bolting patterns can be provided by us. Um, we also provide the torque values, as we said, for the different sizes of flanges, as well as the different types of gaskets, based on the type of bolts that are used. So this is what a preferred and minimum torque values table looks like, that we provide to our customers. So if there are large quantity of bolts, numbering the heads of the bolts is a good technique to keep track of which bolts we have tightened, and if we have lost some type of some or the other nut while tightening. So, and we also make a final pass in the clockwise direction to ensure all bolts are at the final torque. And again, this is the legacy star pattern for 4 bolts. It's called legacy since it is a old method, and this is still used, and it is perfectly fine. So hence it's called the legacy star pattern. This is for the 4 bolts. This is for 8 bolts. The pattern similar for 12 bolts as well as 16 bolts. One advice that we'd like to give is that the bolt load should only increase and never decrease on the gasket. You need to keep this in mind. Unlike steel bolts and steel flanges, which are elastic like springs, gaskets are by definition deformable and generally non-elastic. Yes, rubber gaskets will indeed spring back if compression is reduced, but under long-term pressure, it will be permanently thinned in the area under load. So as the joint is drawn together, it is important to minimize any decompression of the gasket during the installation, because once compressed, these gaskets will not spring back into its original thickness to form a seal. So bolts must be tightened in gradually increasing steps in an effort to only increase and never decrease the load on the gasket. One failure that we have come across at one of our clients is that the flange connection was torqued at high values. However, they did not use any hot bolting. The torque values recommended was 574 Newton meter. In terms of foot pounds, it's like 424 foot pounds. But the used values at the installation were almost past the double of that. And the reason stated was to avoid retorquing, to avoid hot bolting later on. So the media contained in this line was hydrocarbon, and the process flow stream had a high flow rate of 175,000 kgs per hour. So this extreme amount of torque that was applied by the installation That was almost double the amount of the recommended torque. That caused basically this high amount of torque crushed the gasket and caused it to buckle into the process stream, and eventually the gasket failed and the line had to be opened prematurely. So to avoid costly failures and introduction of the gasket and metal debris into the process stream, it is recommended to follow the proper installation steps, and especially in their exact order, so as to not have this kind of a failure. Um, Again, going ahead, this is where we have completed the 6 stages, and the only last stage remains, that is the closing of the system. I'd like to ask you what type of cathodic protection is used at your industry, if it is used. I'd like you to put in your inputs. I see a few responses for galvanic or sacrificial anodes cathodic protection system, but more responses are for the impressed current cathodic protection system. This is again, this was uh, what we envisioned. This is what we imagined. Impressed current cathodic protection systems are generally used widely in the industry. Some places, older pipeline systems do have the sacrificial anode system, and but this is generally not for piping systems nowadays. So going ahead, uh, talking about the closing of the system. The joint closing operations are simple. The first step is to close the bolts once we have tightened, and we can say that the line is completely patched, and we have successfully closed the pipeline. However, the work is yet not done. We need to test if this pipeline holds good, if the installation has been correct. We have to perform a hydro testing as well as cathodic protection testing. If it's an insulation joint, we need to know if the joint is perfectly insulated or not. Otherwise, there's no point in putting in a flange isolation kit instead of a basic gasket. So it's very important to have the cathodic protection testing. Uh, so yeah, um, uh, common hydro testing. As you can see, the common hydro testing arrangement is there in front of you. Here you can have a 3/4 inch vent valve for hydro testing, where you can connect the water connection to it. You can go up to the working pressure or the design hydro testing pressure, and you can introduce the water into it. You can use the vent valve to basically remove the air entrapped in the piping system. And once that has been done, you leave the fluid inside till the like designed duration for the design duration, so that the pipeline can be checked for any leaks that are occurring there. Uh, so once the pressure is held for and you do not see any loss of pressure, you can rest assured that the pipeline is sealing. If there are any loss of pressures, you need to find the leak where from where the system is leaking, and you have to patch it up. If the flange itself requires retorquing, then you would have to retorque the flanges. But for that also you need to first depressurize and again do the retorquing, and then pressurize again, and then check for any leaks if there are any. Going ahead, these are some of the isolation testing equipments that are used. We have the radio frequency isolation tester. We have the ohm meter as well as the potential measurements. We're using different reference electrodes. So these are usually utilized by the compression testing, the cathodic protection testing team. Once they give a go ahead, you know that the flange is perfectly isolating, as well as it's perfectly sealing. Now you can go ahead and repressurize the system and basically energize the system again. Going ahead, once this is done, you close the permit of and give hand over this entire pipe line over to the operations team. Yeah, this is where your work is complete. However, one thing still remains, as we talked about, retalking. Yeah, the need for retalking is that the gasket creep, as we talked about, gasket creep can be as much as 20 to 50% of the gasket thickness, depending upon the material. Creep generally happens within the first 4 to 6 hours after assembly. It generally does not repeat because the gasket material reaches a stable density and resists further thinning. So retightening of the bolts to the same original torque value must be done at some point after the installation to account for the creep. But the retorquing should wait at least 4 hours after the original installation. If that is not possible, then control tightening to the upper limit of the recommended gasket stress range must be done so that even after the creep relaxation effect, there will still be sufficient gasket load to maintain a seal. But special attention needs to be given to the upper limit. It should not go beyond that. Again, system should be shut down with proper lockout, tagout procedures prior to the retorquing operations. So the other way is to do hot bolting. Yes, hot bolting is another method, but yeah, we do not recommend hot bolting as we do not consider as a flange installation best practice. So this is where after the retorquing, we hope that the flange installation is working perfectly fine. And flange management is a vast subject and continuously developing field. With this, we have covered the flange installation best practices in a as brief a manner as possible. Thank you guys for joining in for this web-based webinar. If you have any questions, please feel free to ask them now. We hope for a safe, effective, and economical operation of your installation and facilities. Over to you, Rajesh. Hello, Rajesh. Over to you.
Hi Hamza. Thank you guys. Thank you for joining us. If there are any questions, please let us know in the chat box or in the Q&A section, and Hamza will be happy to help you with them. We'll give them 2 to 3 minutes, Hamza, and then we can log off. Okay. I think there aren't any questions coming in, so we can end the session now. Thank you once again, everyone, for tuning in. Have a good evening, and take care. Bye bye.